Alrighty, welcome back to operating system. So inodes today. So how files are actually stored. We actually get to learn what ls does today, so that'll be fun. So here's what an inode actually is. It's how you represent the file on disk. Last lecture, we ended up with that index node that essentially just is a block full of pointers, and we said that it could only support a file up to 18 megabytes. That's not very great. So this is how files are actually stored. So it's called an inode. It has all the information about the file, so the mode, so those are like the permissions, read, write, etc. Owners, so each file is owned by a user and a group. Timestamps, which are just stored on the inode itself, so like when you modified it, when you created it, which you can change at will. So if you want to make your thing, if you want to make your files created in 1970, you can. The number of blocks that this file takes, and then this gray area is actually pointers to blocks that stores the information or the contents of that file. So there are some pointers that are just directly point to a block, and that way accessing those blocks is really fast because I don't have to read any other blocks from disk to figure out where they're pointers. So there's going to be a set number of direct blocks, so that's just pointers directly to a block. In the case of inodes, there are 12 direct blocks. So there are 12 pointers that point directly to the block. So the first index, or the 0th index here, would be block 0 of that file. The next index would be where the block is for the next index, so on and so forth. Then there is one pointer reserved for single indirect, and that's the idea of index nodes we had before. So it points to a block that is just full of pointers to other blocks, and those pointers will point to blocks that actually store the data. And then if we want to have a file that's bigger, so bigger than that 8 or 16 megabytes, then we go on to double direct, which is like having 2 levels of page tables. So it will point to a block, and because we followed it through the double indirect block, well, this is full of pointers that points to another block that's full of pointers that finally points to the data block. So we can use more blocks for the file. And if we have an even bigger file, there is triple indirect blocks that will do the same thing, just with another level. So any questions about that one? It's pretty much page tables, yep.
So what's the difference between the data in the single indirect and the data in the direct tables? Are they like the same kind of stuff?
Yeah, so the only difference here is in terms of speed. So if it's in a direct block, to figure out where block 0 is in the file, well, I just have to look at the inode and it points me to wherever that data is directly. I don't have to read another block from the disk, which would be slower. So I can store up to 12 of them, like the first 12 blocks of the file, really fast. I can look at the inode itself. And then the single indirect is that idea we had before of just going to a block full of pointers, but I would have to read that whole block in.
So the same file we use all of these?
Yeah, so this represents the contents of a file. Yep.
Okay, is there redundancy between the direct blocks and the indirect blocks? So will like the direct block point to some data that's also just...
Nope, there's no redundancy in it. So the direct blocks are like the first 12 blocks, and the 13th block would be the first entry in the single indirect block. So the idea is that, well, more levels is slower, so I'll use as many levels as I need to just represent that. And I'll fill up all the fast ones before I fill up the slow ones. So whatever block index 13 is would be the first entry in the single indirect one. Yep.
This is for all the files in the file system, not just a single file. Or
No, this is for a single file. So these blocks are the contents of that file, like the index thing, so they're listed in order.
so like in a directory, there's like multiple inodes.
Yep, in directory there'd be multiple inodes, and we'll get to play with them today.
Okay, is there anything more than triple indirect, like quadruple indirect?
There could be, but let's do the calculation, see how big a file could be if we did triple indirect. Oh,
This is for like one file, like maximum size of the file would take up all the direct, single indirect, double indirect, and then triple indirect blocks.
yep. Yeah, maximum size of a file would be if we fill up all of them. Yep.
Maybe this is a little off course, but like when you try to attach files onto emails or stuff, there's a limit. Is it because of the limit of indirects?
So file limits is like for emails and stuff, that's because the server has a limit. So the server just doesn't want you to fill it up. The file, you can try and upload a file of any size, but it's up to the server to actually just reject it if it's like 12 terabytes of garbage or something like that. So that's just a server limit. Yeah.
Does the term inode refer to like the whole thing starting from the node, or is it just the?
Yeah, so the inode refers to this entire structure. So this is everything about a file you could want. So all the timestamps, who owns it, permissions, and where the contents of the file actually are. Yep.
If we had like a really big file, would we be able to use multiple inodes?
Nope. Yeah, if you have a really big file, you can't use multiple inodes. Just use one inode, but you'd probably be in the triple indirect land where you just have to start using it. So let's, oh, yep.
Are the direct block, single indirect, and all of these like blocks, are they the same size?
Yeah, all the blocks are the same size. So it's whatever the block size on your disk is. Okay, so yeah, so the idea behind this, like I said before, if it's a small file, you just use direct pointers. If it's a larger files, well, then I have to resort to using index blocks, and it's a bit slower, but I'll use as many levels as I need to actually represent the file. There's actually an optimization here, so if the file is really, really small, well, it actually stores the contents of that file on the inode itself, so it uses that space for pointers, and you will discover that in Lab 6 because you will be making that optimization as well. So some files might not actually consume blocks on the disk if they're really, really small. So here's our inode problem. So our index block, usually it stores 12 direct pointers, one single, one double, and a triple indirect. So if our block disk size is 8 kilobytes and a pointer to a block is 4 bytes, and indirect blocks only consist of direct pointers, there's no metadata or anything like that, what is the maximum size of file managed by this index block? Well, we can have 12 8 kilobyte blocks through direct pointers, and then through the single indirect, well, if we fill up a whole block full of pointers, it's 2 to the 11, so we can fit 2 to the 11 on a single block, so it'd be 2 to the 11 times the block size, which is what we figured out before, which is 16 megabytes. And if you go through, well, here's the number of pointers for our indirect table. It's just how many pointers we can fit on a block. So the total number of addressable blocks is 12 through the direct, 2 to the 11 through just the single indirect, and then through double to indirect, it would be 2 to the 11 to the power of 2 because each of them can point to another block that's full. And for the triple indirect, it's the same thing, but to the power of 3. So this 2 to the power, I can be lazy, this 2 to the 11 to the power of 3, well, that's going to be the dominant term. So if I want to estimate the maximum file size, it's about that, which would be 2 to the 33. And then if I multiply 2 to the 33 by the block size, which is 2 to the 13, that means the maximum size of the file is 2 to the 49, or 64 terabytes. Seems a bit more reasonable than 16 megabytes. Yep. So the inode itself would also be stored on the disk. So you'll also figure this out in Lab 6. So the file system will set aside some blocks to just store inodes. So there'll be essentially just a giant array of inodes stored on some blocks. So they'll be stored on separate blocks, though. All right, any questions about that? So that seems more reasonable for a file size limit. So this is your limit right now on Linux. A single file can be up to 64 terabytes. Past that, if you want a bigger file, yeah, then you have to go to quad indirect blocks or something like that. But this should keep us okay for a while yet. So any questions about that? Pretty big file. All right. So now we get to discuss what the hell a directory actually is. So we have to talk about what a hard link is. So a hard link is a pointer to an inode, and guess what? This is what a file that you see is. So the names in your directory, they're not the files themselves. All the names are in a directory is just a way to refer to an inode. So todo.txt, if I create a file like that, it will point to an inode, and that inode describes that file name and describes where it is on disk, who owns it, and everything like that. So directory entries, aka just a file name, they're called a hard link. Hard link is just name to inode. So any questions about that? So that is what is in our directory. So we can play with this. So multiple hard links can actually point to the same inode. And deleting a file only removes a hard link. The file can be hard linked somewhere else. You might notice that there is, if you look at the system calls, there is no system call called rm or delete or anything. The closest thing is something called unlink. So we can play with this a little bit. So let's create a file called todo.txt. Say hello there. So we've all done ls before. So if I do something like that, do we know what all these things actually mean? Here, I'll get rid of the A. So do you know what all those columns actually mean for this file? Yep, ish.
I can kind of guess.
Okay.
The first stuff are the permissions for the owner, the group, and something else. The user.
For everyone else, yeah.
And
Yeah.
then, I don't know what the number is.
Mystery number, okay.
And I think that's just either like the user who created it, I believe.
So that's the, yeah, that's the user owner. Then that's the group owner.
And then that's just the timestamp, I believe, or
So there's 13.
that I don't know anything.
Size of the file. And then here, timestamp probably when I last modified or created it, last modified it, and then the name. Okay, but we don't know what this number is. Anyone know what this number is? All right, let's give you a hint. So you can create hard links if you want through a command called ln. So ln will create a hard link, and the first argument is, well, a name, and you take whatever that inode or that name points to, whatever inode that points to, and you can create a new name that also points to the same inode. So I'll create b.txt. So now if I look in my directory, I have todo.txt and b.txt, and they both point to the same inode. So if I look at the contents of b.txt, if they point to the same inode, and inode describes everything about the file, including its contents, what should I see? Yeah, hello there. So I do that, I see hello there, and it looks the exact same because both of these names refer to the exact same inode. So I'll do ls again. We don't know what this number is. Do we have any guesses now? Yeah, number of references to this inode. So that's what that number actually means, which I assume no one would have any idea what that meant before this lecture. If you did, you didn't need this course. Yep.
So what's the difference between this and CP? Is it just copy as well?
Yeah, so what's the difference between this and CP? So let's learn another ls switch. So if I add I onto this, it will create a column for me that tells me the inode. So if I do this, this column is now the inode that that name refers to. So I can see here that both b.txt and todo.txt refer to the exact same inode. So you were asking about copy. So if I do something like this, so what should that do? If that's making a complete copy of the file, would that be a new inode or point to the same inode or what? New inode, right? Because I can modify c.txt independent of todo.txt, so it should be a new inode. So let's just verify that. So yeah, we can see c.txt is now a new inode. There's only one thing pointing to it, which is c.txt. So copy would create a new inode and then make that inode look exactly the same whenever it copied it. But otherwise, after that, it's kind of like forking. They're like independent at that point. So it just copied it. Now they're independent. All right. Yep.
If you make a shortcut, is it the same thing as making another hard link to an inode?
So shortcuts are slightly different, and we'll explore them next because they get another fun name. All right. Any more questions about this? All right. Well, also knowing that number, we can see that, let's go I. So dot and dot dot are just names in the directory, and they also have inodes. So each directory also gets an inode, and we just said that this is the number of things that point to it, number of names that point to this inode. So this is 2 and this is 3. Why would this be 2 for dot? So why is the number of links to, or the number of names to the inode of dot equal to 2? Yeah.
I would guess that it's because the parent directory can point to it and it also points to itself.
Yeah, so dot is itself. So that's one reference to this inode because dot is always the current directory. And if I back up one directory, I do the same thing. Well, there's a directory. In this directory, that inode is called test directory. So it's called test directory here, and it refers to the exact same inode as dot. So that's the second reference. And dot dot, well, that refers to this 28 inodes directory, which also has a parent, so that's why it's 3. So you can also see how popular your directory is through doing the same thing and counting, how many references are there to this actual directory. All right, so any questions about this before we carry on and make our lives even more, well, more fun? Yep.
The last thing you said is like, so we have like 2 references to the current directory and then 3 to the parent.
Yep. Yeah, so 3 to the parent because dot dot in this directory refers to the parent. In the parent, dot refers to itself. And then above the parent, it has a name, right? So that would be 3. Yeah. Yep, so if I make directory okay and do the same thing, now, yeah, dot went up to 3 because now I'm the parent of this directory. So it increased the count by 1 because in that directory, dot dot would refer to this directory too. So you can see how popular you are. So if I created another one, same idea, goes up to 4. You can see how popular you are by that number too, I guess. All right, any other questions about that? Let's remove those. Yeah.
Is this one way of determining the number of contents in some directory?
Yep. Yeah, you can see, well, you can see how many directories point to you. So, all right, so, all right, soft links are shortcuts or symlinks. So they have several different names depending on what operating system you're using and what you want to call them. So usually in Linux, shortcuts are called soft links, or sometimes they'll be called symlinks. So if I say symlink or soft link, they refer to the exact same thing. So all they are is instead of a name pointing to an inode, it points to another name. So if I create a soft link called b.txt, I can point it to the name to-do.txt, and then for the kernel to resolve this, well, if you refer to b.txt, it knows to look up to-do.txt, and through that, that would have to eventually be a hard link that points to an inode that actually represents something. So soft links don't really need to exist. They can have some flexibility, but it gets a bit weird. So it's just a name, so whatever they're referring to, you can just delete it or get rid of it, and the soft link will now just be broken, and if you try to use it, it'll just give you file not found. Let's just play with it for a bit. So, so what do we have in this directory? Let's just get rid of, oh wait, before that, let's get rid of b.txt. C is a copy, okay. So let's create a new hard link called c.txt, just to make sure that we understand it. So to do.txt, it says hello there. If I go ahead and I make a hard link called c.txt for it, and then through c.txt, I modify it, what happens if I try to look at the contents of to-do.txt? Yeah, it should be modified as well because that's the file. So I can modify it through different names, doesn't matter as long as it just goes to an inode. An inode actually represents the contents of that file. So a soft link is the same command, but you do a -s for soft link or symlink, whatever you want to call it. So I can create a shortcut, soft link, symlink, whatever you want to call, called b.txt, and it will be b.txt should refer to to-do.txt. So if I look at it now, shortcuts or symlinks show up as just a name to a name. So now if I try to refer to b.txt, it will give me to-do.txt. So if I cat it, it'll go ahead, give me hello all. But you'll see here, if we do ls-i, it gets its own inode. So technically that to-do.txt has to be stored somewhere. So that's stored on an inode, but it's really small. So that's where optimization comes in. It has all permissions because, well, all you care about is what it points to. The permissions just protect the name. So generally you just give it all permissions and that's the default. And that's it. So whenever I refer to b.txt, kernel will go to to-do.txt to find the inode and then finally give you an inode if it's there. So the reason why we have this is if you have hard links, everyone remember what a DAG is? A directed acyclic graph. So your file system is a DAG, but with symlinks, you're allowed to create cycles and everything. So it's a bit more flexible like that, and it's more fun. So if I wanted to create a cycle, what's an easy way to create a cycle that is infinite using symlinks or soft links, whatever you want to call them? Back to B, all right? So I could do something silly. I could get rid of to-do.txt and create to-do.txt that points to b.txt. Now you can see I made it mad too. I guess that's new, but I create a cycle. So if I look at b.txt, it'll say, oh, go to to-do.txt, and then in to-do.txt it says go to b.txt. What do you think happens if I try to look at the contents of either of those files? Crash. Yeah. The sizes? Yeah, so the size of the inode that represents your symlink is the size of the name it's referring to. So to-do.txt is 8, b.txt is 5. So it's the length of the string, because technically that string needs to be stored somewhere as well. Yeah?
Sorry, so you said inode was stored somewhere on the disk.
Yep.
If you did that, is that inode just lost?
No, so wait, which inode?
To-do.txt, the file, the hello file.
Yeah, so right now that, I think c.txt pointed to it because it had hello all in it. So c.txt still had a reference to it, so it didn't get deleted. Yeah.
What if you didn't have c.txt?
Yeah, if I didn't have c.txt, well, then I have no references to that inode, and then it might actually get deleted. So this rm command, here we can, so right now I have 2 links to this file. So if I do rm doesn't actually delete anything, right? Because I can delete one of those names. The file's still around. It exists as long as there's a name referring to that inode. And if I even strace rm, I can see that the system call it used was unlink. All unlink does is remove the name from the directory, and that's it. So as long as there is, that's why it needs to keep track of the number of references to that inode. So as long as there's at least one reference, that inode should still be active and it shouldn't be deleted. And this is also kind of how your recycling bin works. So what your recycling bin how your recycling bin works is, well, instead of whenever you remove a file, your recycling bin can keep a reference to that inode just in case it needs to bring it back. So as long as your recycling bin has a reference to that inode, that the contents of the file won't ever be deleted, right? And to restore it, that's why to recover a 20 gigabyte file from your recycling bin, it takes no time at all because all it does is recreate the name, point to the same inode, that's all it has to do. Doesn't matter how big the file is. Yeah.
So as soon as you lose the, as soon as you delete the last reference,
Yeah.
the OS knows to just delete the inode?
Yeah, as soon as you lose the last reference, the kernel, that's the one keeping track of anything. So if it wanted to, it could delete that contents. Turns out deleting contents is slow, so it would technically just leave it alone on the disk and just mark it as unused. And that's also why you can recover data from drives, because, well, actually deleting it is slow, but you might notice that even if you delete all references to it, as long as you're really, really quick, well, the inode might actually still exist somewhere. It's just marked as inactive, so it's just a process of scanning all the inodes and seeing if it still refers to something. And you can recover your files that way. So that's how data recovery works, and some people make a lot of money doing that. Yeah.
So if you put something in recycling bin and it'll just like, it'll keep the reference, doesn't that mean you're not actually like you're not restoring any space?
Yeah, you're not restoring any space or anything. It still exists, but it's better than being deleted, right?
Then what's the point of the recycling bin? You could just keep it around.
Yeah, so the recycling bin will delete it, get rid of its reference after like 30 days or whatever, or whenever you say clean it up, and then it can actually free that space. Yeah.
What's the point of soft links then? Like, is it just like a shortcut? Is it a real file or?
So soft links are a real file, but they just refer to a name. Sometimes that's actually a useful thing. So if you want to, it gives you like another layer of indirection. So you could have essentially a shortcut to, I don't know, one example is like you could have a symlink called Python that points to the actual Python binary, right? And if you want to upgrade your version of Python, all you have to do is change that symlink, and then everyone starts using the new Python binary or something like that. And it's more flexible that way. So that's one way. If you look at your VM, your Python executable is probably a symlink. Your compiler may also be a symlink. A bunch of other things are symlinks. It just makes changing things a lot easier. And it's just kind of nice sometimes. Yeah.
So if you delete a hard link that a symlink points to, what happens to that symlink?
So if I delete, oh wait, so first keep that thought. Let's look at our cycle. So let's try and cat b.txt. What do we think? We think this is just an infinite loop and our kernel's dumb. But now, well, was the kernel smart or was cat smart? Cat was smart? All right, so if our guess is cat was smart, what would we use to see who's smart? strace. Let's strace cat and see what it did. So, we got too many levels. Open b.txt, too many levels. I only opened it once. The kernel is smart. So you can see it never even tried to open to-do.txt. I just did an open system call, and it got -1, so it got an error, and my error was eloop, too many levels of symbolic links from the kernel. So the kernel is smart. And the kernel will stop you from hurting yourself, I guess, because this could be a very complicated number of links, like loop of symbolic links. I could get up to like 20 and point it to the next one. So the kernel is the one that's smart. Plus, makes sense. You wouldn't expect every single program to deal with symbolic links and do it properly. especially if they don't even know what symbolic links are, because I could have given you guys symbolic links and done this to you, and would you have ever figured it out? Probably not. All right, so what was the other question? If I just delete a symbolic link? So
If you delete a hard link that a symbolic link points to.
So a symbolic link will just point to another name. So I can't delete the inode it refers to. So here, let's get rid of stuff. So c.txt. So I'll recreate to-do.txt. So what do you want me to delete here? So just delete to-do.txt or just remove it, unlink it. So if I do that, then b.txt is just named to a name. It's still going to point to to-do.txt. To-do.txt just doesn't exist anymore. So if I try to cat this, it will also look kind of confusing. So I'll say b.txt no such directory or file, which gets a bit confusing because b.txt does exist. What doesn't exist is to-do.txt, so it gets a bit confusing. All right, any other questions about that one? We've kind of figured it out. So, So yeah, what about if we did all of this? So touch will just create a new file and reset all of the parameters of it, like all the timestamps. Then here we create a hard link called b.txt to refer to the same inode as to-do.txt. Then if we create a soft link called c.txt that points to to-do.txt, and then, yeah, similarly for move, all move does, it doesn't move anything. All it does is rename that name. So it doesn't actually move anything. That's why no matter how big the file is, move is fast. So it doesn't matter because all it's doing is changing the name. It's not changing the inode or anything like that. The contents of the file stay the same. All it does is just change the name, points to the same inode. So now if we do remove b.txt, well, what does the file system look like before and after the remove commands? So for this, before the move, we would have c as a symlink that points to to-do.txt because soft links or symlinks are name to name. And then to-do.txt and b.txt refer to the same inode. So if I do this move, all I'm doing is changing the entry called to-do.txt to d.txt. So, or to d.txt. So now d.txt and b.txt refer to the same inode, and c.txt, because it's a soft link, just refers to the same name, to-do.txt, which doesn't exist anymore, which is the exact same thing we just saw. So now if I do the remove b.txt, well, it's going to be the same thing. I just remove that name. That inode still exists. All my data still exists. I'm all good. So any questions about that whirlwind of ls? And other things you can do too that are fun is if you want to see information about a file, like all the information that's on the inode, you can use stat. So if I stat c.txt, it will tell me, whoops. So if I stat c.txt, it'll tell me all the information about it. So so this is the name that I refer to it in the directory. That's not on the inode itself, but all the rest of this information is on the inode. So it tells you the size of the file in bytes, the number of blocks it takes, which looks weird that my file that's 10 bytes takes up 8 blocks. Why wouldn't it just take up 1? Well, ends up it does, but for some reason, don't ask me why, when that refers to blocks, they are of a set size. So those blocks, for some reason, again, don't ask me why, they are 512 bytes. Why? I don't know. They're just hard-coded at 512. This tells me my I/O block size, so that's my real block size on a device. So if I take 4096 and divide by 512, that's where the 8 blocks comes from. So it only actually takes 1 I/O block, but it takes 8 512-byte blocks because that's their weird hard-coded value, and don't ask me why, because I'm not that old. Although that's debatable, I guess, to you guys. And then it'll also tell you some other information that we kind of gloss over. So the device is what physical device this file is actually located on. So if I had multiple drives, it would have a different number here. Then it has the inode number itself, the number of links to it. This is the mode, and then the owner with the user ID, the group owner with the group ID, and then timestamp. So this is when it was last accessed, so last read, the contents of the file. This is when the contents of the file were last modified. This change, you might think change and modify mean the same thing. So this change means if the inode itself was changed. So modify is the contents, like the actual contents of the file, and change is any modifications to the inode itself. Why it's kind of confusing, I don't know. And then birth is whenever this inode was originally created. And all of these timestamps you can change at will if you know the correct system call and you have permission. So that's why generally I don't really care about timestamps because you could change them. If I wanted to, I could change it to I created this file in 1969. And yeah, that was way before I was actually born, so don't make jokes about that. So yeah, you can just change these all you want. In your lab 6, well, you'll be creating inodes, so you can put whatever time you want. The marker just checks if you have like a time of the same right year, because yeah, but you can put whatever time you want there. So any questions about this stuff? So if you've like an elective course, cough, cough, and you can change the timestamps and be like, yeah, totally submit it before the due date. So maybe this course has made me less trustful, but yeah, timestamps are just data on the inode. Yeah.
Somewhat off-topic question. Is that all those numbers after the dot, are those still time?
Yeah, all the numbers after the dot.
That level of precision?
Yep. Yeah, so here, so like these numbers, right?
Yeah.
Yeah, so the timestamps have like nanosecond level of precision sometime. Why it needs to be that precise? But they are that precise on some systems. Mostly they went up to like 64 bits and you can shove a lot of information in there, so I guess someone figured why not. I think originally they were millisecond level, but hey, now they're like nanosecond, which I guess is cool. Do you really need that? Probably not, but if you want to see the nanosecond granularity, you can use stat. Yeah?
How do you modify these stats?
How do you modify them?
Like, you said we can change the dates, like you know what I mean on our assignment.
So yeah, you can use the touch command. So touch actually just modifies the timestamps, and here, stamp. Use this timestamp instead of the current time. Modify whatever you want, access time, modified time, whatever you want. So touch will do that. So let's see, if I just stat c.txt, I can see all of the timestamps are like 14, 21, 40, 30. If I do touch, if you give it no arguments, I think it just sets it to the current time, all of them. So let's see if that's real. So yeah, it doesn't change the birth, but it updates the modify, access, and change time all to be whenever I just ran that touch command, and they're all the same. But you can, that's essentially what the touch command does. But at the end of the day, it's just a system call that you make. As long as you own the file, you can change whatever you want about it.
Would that overwrite your previous c.txt running touch again?
Nope. So all touch does is update these timestamps. It doesn't change the contents of the file or anything. All right, any questions about that? I probably shouldn't have taught you that. But, I mean, it was one man page away. So, in Unix, everything kind of looks like a file. So directories also have an inode, and there's nothing special about them except the contents of a directory just have to follow a specific format. You'll find out that directories, all they are essentially a list of tuples, and the tuples are just name to inode, and that's all a directory is. It's just full of name to inode, that's all a directory is. So however many entries are in the directory, well, that depends how many names are in this directory. So for example, right now, if I ls-la, the actual directory, which is like this inode, this inode whatever 60 at the end, well, that would have the contents of that inode would actually be like dot to this, dot to this inode, b.txt to this inode, c.txt to this inode, and that's all a directory is. It's not special. Yeah.
I remember in last lecture you talked about like Vnodes, which are like pointing to inodes. They how does like a hard link or?
So the vnode can represent different things like a socket or a pipe or anything like that. So in the case that your file descriptor refers to an actual file, that vnode will actually be an inode, because that's how it can access the bytes of this file through an inode. So if your file descriptor is a real file, that vnode is actually an inode, which is cool. Now we figured out how that kind of works. All right. Any other questions with that stuff? Yep.
Wait, so is the vnode the inode, or is vnode the name and the name points to the inode?
So the vnode is just like a virtual node. In the case that that file descriptor represents a real file, the vnode would be an inode, because that's how I access those bytes through the inode. That knows where they're actually located on the disk and everything like that. Yeah.
E means virtual node, right?
Yeah.
What does I mean?
Index node. Yeah, so I index node, because we started off with the idea of an indexed allocation. That's what this is, essentially just multiple levels and slightly complicated. Although it's not bad after we have got through the hell of page tables. So basically the same idea as multi-level page tables. All right, so we can do a quick quiz. So what's stored on an inode? So quick, is the file name stored on the inode? No, you're right. File name, where's the file name stored? In the directory, right? Because the directory is just name to inode, and that's where the names exist, just in the directories. So the containing directory name, is that in the inode? Nope. Yeah, that's just within the current directory. It would have an inode or a name called dot that refers to itself. Is the file size in the inode? Yep. Is the file type in the inode? Well, spoiler, yeah. Number of soft links to the file? Yeah.
How is the file type in the inode? Is it less than a name or something? Like the first 3 or 4 bits, I think?
Yeah, so there's a few other bits that you'll see in Lab 6 that tell what type of file this is. For inodes, basically inodes can be like soft links, directories, or regular files, and that's stored in the inode itself. So it has like 3 options, and you'll see more of that in Lab 6 too, because you get to create your own inodes. All right, so the number of soft links to a file, that's not stored in the inode because, well, they're just names in the directory that point to other names. The location of the soft link, also not in the inode. What about the number of hard links to a file in the inode? Yeah, so that's that links one, and if the links drops to 0, then we can actually delete it, although your operating system is probably going to be lazy and just mark it as unused because it's actually slow to delete a file. What about the location of the hard links? No, not really. Access rights? Yep. Timestamps? Yep, and I accidentally showed you how to change them. What about the file contents? They point to the file contents. In the case that we optimize it and it's like really short, it might be, but that's like a little caveat. What about an ordered list of data blocks? Yeah, well, that's kind of what the pointers actually are. So let's see if we're right. So yeah, so soft links we don't know. Number of hard links we do know. The location of the hard links, the inode itself doesn't know what names refer to it. It's just a dumb data structure that just points to the contents of the file. So if you just know an inode number, well, from the inode itself, you don't know what names actually refer to it. You'd have to walk the entire file system to figure out all the names that refer to that inode if you want to. Yep.
So the directories, they store like the tuple that you mentioned, but
Yep.
they don't store the soft links or like what they do with soft links because they're just named.
Yeah, so technically, a soft link is also an inode. So I said name to name. That's just a shortcut. Technically, an inode or a soft link is name to an inode that inode has a name.
Okay, so in the inode, we have like the soft link name.
Yeah. Yeah, so in this case, this inode, which points to a name, the contents of that inode is just to-do.txt. So it really looks just like a file, like the contents, but you just interpret the contents of the file as a name instead. So here, the size is 8, so the symlink itself would be an inode, so a directory is only name to inodes, and it's a bit of a roundabout process because technically a soft link is name to an inode, and that inode points to the name. But usually when you think about it, you just think of a soft link as name to name because that's how you use it. The intermediate step doesn't really matter that much. Yep.
So if you were to do nano b.txt, and assuming that b.txt was like a valid soft link, would that edit the to-do.txt file?
So if I just go ahead and create to-do.txt, so like right now if I edit b.txt,
Yeah.
so yeah, if I edit b.txt, well, it would follow me through to to-do.txt, then get that inode, and then that's where things are actually stored. So yeah, if I modify this, then it should actually modify to-do.txt because I modified the contents of that inode. So if I cat, it's the same thing, right? Because I eventually get that inode. The only way to actually like change the contents of the soft link itself is just changing the name if you wanted to. I don't know if you can open it in an editor. Oh, wait. What's my soft link called? Oh. Yeah, so sometimes you can tell programs to not follow soft links because that's one level of exploit for some web servers. If you can just upload any random file, well, an attacker, if you allow symlinks, can just create a symlink that brings them up to root, and then they can access any file on your system through that symlink. So generally, web servers will turn off following symlinks. So if you put a symlink in a web server directory, the web server won't actually follow it. But that's like a fun security fact. Because yeah, soft links, if you just let users create soft links, that's not great. All right, well, we used a lot of time, oops. So file systems are going to cache data blocks and try and speed things up. They're going to be lazy. So one thing, like writing data to the disk is slow, especially since to modify it, I would have had to read it into memory. So what they do is just use a cache. So file blocks that are cached in main memory, there'll be some file system cache to cache the blocks I read in from a device. And generally, whenever I'm reading blocks, if I'm likely to reference the same block over and over again, so if I'm modifying a file or something like that, so using the same block over and over again is something called temporal locality. So I just used it, it's likely I'm going to use it again. And logically, if blocks are near each other, you might use them. So if I open the first block of a file and I'm modifying the entire thing, I'm probably going to modify the second block of the file. So if I want to speed things up, I can just read multiple blocks at a time or prefetch them and load them into memory so things get faster. So what your kernel could do also is whenever you modify a file, it could just write it to memory and not the disk and try and fool you into thinking it went really, really fast. And there can be a kernel thread that actually does the writing to disk in the background when it's otherwise not doing anything. So sometimes when you modify a file and then you pull out the power cord, well, your disk is supposed to be persistent, but if it was actually cached and it didn't write it out, you might not actually see your changes on the disk. And that's what the commands flush and sync do. They will trigger and force that write cache to clear out and actually write to the device. I've encountered this a few times, and we're probably over time, where I copied file to a USB drive and it happened instant like that, even though I knew it was a crappy USB drive. And that's because all it did was fill up a cache and didn't actually write it to the device. Then I called sync, and then it took forever because it was actually forcing a write to the USB drive. And with that, we're out of time, so just remember, poem for you, we're on this together.